Claudia and Wajia are two of our PhD students who are almost finished at in Münster. And so they prepared for the plan map meeting last year also a really nice set of slides to show the different kinds of morphologies that we can see on the moon, to get everyone kind of an idea of what features we're going to be looking at there. And so I've taken their work and combined it with some additional information for everyone about the morphology and geologic mapping of the moon. What I want to do today is to basically give you, again, sort of a logical framework for why are we even going to want to make a geological map in the practical session, and what are we going to want to do with it. And so I'll start by showing an earlier version of Claudia's really awesome map of the South Basin of the moon. You can see that this map plate, which is basically an end product, has a lot of information on it. And this is the type of information that you ideally want to work towards when you're making a geologic map. And so what we have here, and I'm sure that you got a lot of details that kind of look familiar from yesterday during the various lectures and practical information about QGIS, is we've got then, let's see, my pointer disappeared. There we go. We've got naturally the map itself, which has color-coded geologic units that represent different kinds of geologic materials that have been marked off and delineated. But also what's very important is that we have this, basically this progression, this time progression of the units that appears in all geologic maps when the units are organized. And here you don't have to be able to see the text. It's important just to see that they are sorted then by color. Okay, and the oldest ones always come at the bottom of this table, and the youngest ones appear at the top. So part of the process of what we're going to do today is have a look at how do you decide which units are younger and which are younger up here and which units are older, and to start sorting those in your mind as you're making your map. Okay, so another aspect of the map chart is some geological profiles. I mean, that basically is just where you take a line across an area of interest in your map, and then you look at the vertical distribution of the rock units. And that's kind of a more advanced step that you can use to add some additional information to your map. And here in this case, it's such a large area that Claudia prepared 3 different profiles. Then we have down here in the corner what's called a correlation chart. And it basically graphically shows you the age and the duration of the formation of each of the units. And we'll have a more careful, closer look at this later too, because all of these things together provide you at the end of your geologic mapping experience the information that you need to understand and interpret the geologic history of your mapping area. That is the goal. You have an area that is of particular interest, and then you want to know, okay, what happened over the 4.5 billion years after the South Pole Aitken Basin formed. There were craters that formed afterwards. There were volcanic events that happened. Mare basalt was erupted. There was a huge basin here that formed, the Orientale Basin. And when you've mapped all of these things out, ordered them in order of age, and then had a look too at the subsurface expression of these units in particular locations, then you can write the story of the history of the South Pole Aitken Basin. So we're of course not going to map the South Pole Aitken Basin today. We're going to look at a smaller part in the practical activity. This map has taken Claudia a couple of years to make and expand. It's actually even a larger map today. So just to give you a little perspective. So now my advancing is not working. Maybe if I just, there we go. Okay. All right. So first, just as a quick review, how do you, just from looking at a remote sensing image, figure out how old the relative ages of your units? And for geology on the Earth, there are 3 principles for determining the relative age. This is principles of superposition. So does your lava flow cover up your sedimentary unit, or does the sedimentary unit cover up the lava flow? And then you know, based on these relationships, that the lava flow is either younger or older. Then there's the principle of cross-cutting relationships. And this is applying, here, for example, you have a basaltic dike that cuts through and truncates off these other units that are next to it. And so in this case, you know that the basaltic dike is younger than the units that it cuts through. And you can apply the same principle when looking at tectonic structures. If the fault offsets the units, then the fault is younger than the units that it's offsetting. And so you just have to use a careful analysis and logic to figure out, okay, what is the progression of the events that happened with your different geologic units. Now on the Earth, there's also the possibility to use index fossils, and that, of course, is not something that we have available on the Moon. But we do have a couple of additional principles that we can use for determining relative age. And one of those is the relative crater density. And we'll talk about that in great detail today. And also there's kind of a bonus. So we have a 4th option, is to have a look at the degradation state of particularly of the craters, but you can also look at the degradation state of other kinds of surfaces to help give you a relative age idea. Okay, and then the goal with all of this, the mapping and the orientation of the units into ages, is that we ultimately want to compare here the Moon on the far right with the geological history of the other planets. And so I've just put the terrestrial planets here. This information is available in this Hiesinger and Tanaka 2020 planetary timescales chapter. And so this is like the super big picture where we're going towards, is understanding the evolutionary history of the terrestrial planets in the context of the entire solar system. So Claudia's map of the SPA basin gives us information about the Moon here now that, for example, we could compare with the development of life on the Earth, and see how those processes and events tie together. Okay, so let's move back to just the Moon for this lecture. And basically, we're just going to look through the morphologies that you're going to expect to see during our activity. There are 3 major landforms that we're going to see: basins and craters, mare and highlands materials. And so I'm just going to step through here and give everybody an overview of what these look like, and then you'll get familiar with them during the mapping exercise. So let's start with basins and craters. Basically, craters on the Moon start from super tiny, like nanometer or centimeters in size, that can occur on a small grain of glass or something. But for our purposes, for mapping, the craters of importance start here with these simple craters, like this example, which is kind of bowl shaped, and it has some material that has slumped down into it off of the walls. So this is crater fill material that you could decide would be a separate unit. The crater rim you would mark on your map. And then you might or you might not be able to see crater ejecta that you could also mark as a separate unit. We'll see some other examples of that. As craters get larger, there's a transition into from this simple morphology into a complex morphology, and this depends then on the gravity of the moon. This transition happens at different diameters depending on what planet or body it happens on, because it's gravitationally controlled. And so when you get to larger craters, for example, you get a central peak crater like the crater Tycho. And you can see that the crater wall is more complex. It has some terraces on it. And then you have impact melt here in the floor and impact breccias, a central peak. And at Tycho, you can actually well see the ejecta because it's a younger Copernican aged crater. We have other pictures that you'll be able to see that better on. And then as you get bigger, you get to see, we've got 100-kilometer scale bar now. We get into a peak ring crater, for example, the Schrödinger crater. And here you can see that the central peak disappears and that there's this central ring, peak ring structure that starts to form. You still have in the floor impact breccia and impact melt. In this case, also, there's some other material that has come afterwards, light plains unit, for example, and we'll see an example of that. Okay, and then even bigger, you get to a multi-ring basin where Oriental, for example, shows at least 2 rings. And this innermost ring actually has gotten now filled up with some Mare basalt that filled in a bit later after the basin had formed. Yeah, and then you get even the largest on the moon, and one of the largest, or the largest in the solar system, the South Pole Aitken Basin, which is 2,600 kilometers across. Okay, and I mentioned earlier that you can also use degradation state now to get an idea of relative age. So here, for example, is a really degraded crater that is missing part of its rim, and the rim material that's there is really kind of rounded off, and it's not complete in many locations here. This crater also got filled in with some flat Mare basalt material. So here is an old what you would then with practice learn a Preambrium aged crater. And then a crater here that has a bit more of a well-defined rim. And you can see that there's some ejecta material that is still visible close to the rim. This type of a morphology is younger because the degradation hasn't progressed as far. And then again, with experience, you would realize that this is most likely in the Imbrium period, would be classified in that Imbrium period. These periods, just to back up for a moment, are demarked by particular craters that formed, and those craters then are kind of the marker horizons that are used instead of like fossil beds. And so the pre-Imbrium craters formed before the Imbrium basin. The Imbrium craters formed after the Imbrium basin, and the Eratosthenian craters formed with and after Eratosthenes. And Copernican age craters formed after 1 billion. Copernicus crater is the sort of the type crater for this. And this is the only then age that's not specifically tied to this crater. It's 1 billion years and older, approximately. Okay, so we have these pre-Imbrium craters that are really degraded, these Imbrium craters that are somewhat degraded, that the ejecta is basically almost gone. Then we have Eratosthenian craters, which have even sharper rims, and they have more visible and larger extent of ejecta still, although you can see that it's a bit more degraded. And then for the Copernican craters, these are the youngest ones. They have a very sharp rim, and you can see here that you can see this high albedo ejecta, and then also rays that extend away from this crater. And those are the defining marks for a Copernican aged crater, because that stuff disappears really quickly over time. Okay, so I mentioned just on the overview picture some of the morphologies of the different impact units, but here I wanted to give a few more details and a few more closer up views so that you can see it a little bit better. This is Tycho crater again, and so you can see, as I mentioned, this really nice terracing on the crater wall, and then in the flat floor here on the eastern side, smoother impact melt, and on the western side, more rugged, hummocky impact melt that contains more blocks of material. And actually what we find in the end is that this part of the crater is a little deeper. So a lot of the liquid impact melt likely flowed towards this region and then ponded more, giving it a flatter surface over here. Then you've got your central peak, and then the ejecta textures that are just outside. And you can maybe see here some very flat areas. That's also impact melt exterior to the crater. Right, and then we just have an oblique view coming from this direction, showing the central peak and this rugged, you know, it looks smoother than the surrounding material, but it's still actually pretty rugged because there are a lot of blocks of material in it. And so that would be your impact crater unit. Here are some pictures of smaller craters that are high albedo, so albedo views. So the sun is basically coming from above, and it gives you more information about the reflectivity properties of the materials compared with the morphology. These images, when I just step back for a moment, have the sun coming from a lower angle so that you basically see the topography more pronounced compared with when the sun is coming from directly above, where you see then the albedo differences between the material more pronounced. And so here you can really see these really, I mean, artistic views of the ejecta blanket. And then this black stuff here is ejected impact melt that then has overlaid the clastic ejecta and the continuous ejecta. Okay, so there are also, when you get into the details, this is probably going to be, this is higher detail than you might actually want to map. It depends on what your goal is. If you're looking at impact melt processes, you might then want to zoom in and then very carefully map the expression of impact melt that's flowing off of the crater wall into the crater floor, or the distribution of the different kinds of materials that are coming down the crater wall into the crater floor. Here, the black stuff will be impact melt, and then the white stuff is more clastic ejecta. And so, I mean, you could spend hours just looking on Hellrock Quick Map, for example, at all of these beautiful details in the geological expressions on the moon. Here are just a couple of other examples of impact melt flows. You can see that they have well-defined flow lobes that are coming down. Here, it's kind of almost a, well, volcanic type features where you have a channel that was cut through this material by the impact melt flow. And so that's similar to some volcanic channels. And then here we have another example of an impact melt flow. One other thing that can happen in craters that I think we might see in the mapping area is also that their floor becomes inflated, that a volcanic sill basically forms underneath the impact melt and impact breccia, and it inflates and causes there to be this fracturing. Or perhaps also in this case, this crater was filled with Mare basalt, and then a sill formed underneath that layer and pushed it up and cracked it. And so these are called floor fractured craters. They're sort of a special class because it's a hybrid geologic process that happens to form this morphology. Okay, so that was sort of an overview of the morphologies that you're going to see associated with basins and with craters. And now we'll have a quick look at mare basalt features. The mare basalts are simply, these dark areas that are covering the moon. And just even from looking at this view of the moon, you can tell that the mare basalts superpose this highland material and they actually fill in a lot of the big basins. And so what this tells us immediately, without us having to do any special analysis, is that the mare basalts are younger than the highlands and younger than the big basins, or at least concurrent with some of the big basins. Okay, and so they basically, just like the basalts from Hawaii or the Canary Islands or anywhere, they just are plains forming volcanic material, and so they have the smoothest, flattest surfaces on the moon. They have generally a high iron content, although there's a variety of compositions here. They are higher iron in content than the highlands material, and that is reflected also just in their color. The iron is what iron and titanium make the mare basalts dark. And then it's also logical that because these are basalt flows, they're filling in the lowest elevation regions, particularly on the near side here. On the far side, the lower elevation regions aren't filled with mare basalt because there aren't that many large occurrences of mare basalt on the far side. But we will be looking at one of those areas, Mare Ingeni, in our project, in our mapping project. Okay, so we're going to have a look at what features. I mean, mare basalts are somewhat featureless because they're flat and smooth, but there are still interesting things that have happened to them. And one of the examples and one of the major landforms that forms on mare are wrinkle ridges. And here are two examples, here in oblique view, and here looking down, you can see basically what these are thrust faults that have happened while the large basins have sort of isostatically compensated, and these mare basalts kind of slide toward the middle of the basins, and then you have a space problem, and there's thrust faulting that happens. And so you're going to see in the mare basalt that we look at today that you'll find some of these wrinkle ridges. And so if your goal is to do a structural map of a region, then you might spend some time carefully mapping the traces of these wrinkle ridges. And you can actually then do structural analysis on it. We have a couple of students that are working on such analyses in Münster. Okay, and then another feature, but they're not usually observable on the moon, is that in addition to wrinkle ridges, you may see some flow fronts. There are, I think only in Mare Imbrium are there some flow fronts in mare basalts that are visible. Generally, the mare basalts are old enough that such flow fronts have been degraded, and then they're not really possible to see. That's in contrast, for example, with on Mars. On Mars, you can actually there are beautiful lava flow fronts that you can trace and map and do measurements on for a bunch of different analyses. Another thing that you may see in your area this afternoon or later this morning is craters that have then gotten filled in partially by mare basalt. And here you can see that there was a breach in the crater wall that allowed the mare to flow in and fill it. And so again, just another classic example of superposing relationships. Here you've got this little crater rim. It's clear that the mare basalt superposes it. So the Mare basalt is younger. And so then you immediately have an idea of the relative ages between these two units. So you might just then draw a little unit crater rim based on its kind of rounded morphology. You might say, okay, well, it's either Imbrium or pre-Imbrium in age. You can't really tell because any ejecta that might have been there has been covered up by the Mare basalt. But then you start getting an idea of your geologic history for this region. And then you might also have some more features that kind of look like this, where here also it's clear that some Mare basalt has filled in a partial crater. And here probably the topography plays a role in the fact that we just have a partial crater rim that's even just a little bit visible still. So here I would kind of zoom out and check the geologic context for the rest of the region to figure out. But clearly the Mare basalt here again is superposing the crater. Now in the Mare basalt, but also in related other kinds of volcanic regions, there are volcanic morphologies. Yeah, I've got some labels here. Beyond the wrinkle ridges that we talked about, also pyroclastic and lava vents that you can observe, as well as here is a vent and a sinuous rill with potentially a covered lava tube that then either collapsed or there's also cases where we have skylights into tube segments that and I'll show a picture of that in just a minute. Or there are also lava flows that can be seen. So keep your eyes out. Well, and that I don't know if that's a dome or a fragment of, it looks like there might be a little dome here actually. So keep your eyes out if you're looking in a volcanological active region for a lot of these different volcanic features. And I mean, they often are in groups, so you know, they're not alone. Right. Another example of a volcanic feature here is a sinuous rill. This is the Apollo 15, I think Apollo 15 landing site. Yep, exactly. And here also you can see that there are maybe some volcanic sources, these oblong kind of craters. There are not impact craters, but they are volcanic features. Also interesting in this image is that you can see that there are some graben that run through here. So from a structural standpoint, and then also here, there's a graben. And so those are features that you would want to be on the lookout for and could add to your linear feature map that you make for your area. Okay, so here I mentioned just a minute ago that there are a few occurrences on the moon where there's a little skylight that has formed in a sinuous rill, and there's a void space underneath. And so that suggests that this is actually a lava tube that then didn't completely collapse, and that we actually could access that as a cave, which is kind of a really interesting idea. So there are about 3 or 4 of these somewhat larger skylights that are found on the moon. They are much more abundant on Mars, and particularly in the Tharsis region on Mars. And then here's just another example of a volcanic source, and then a short sinuous rill that then kind of peters off into the Mare basalt. When you're looking around, you'll notice that the sinuous rills often end in one of the massive Mare basalt units. And so that certainly then gives you additional information about, okay, the progression of events and the origin of a potential origin for Mare basalts is some of these volcanic vents that we can still see. Okay, I also mentioned volcanic domes. This is a really nice image of a dome that has little domes on top of it. And the classic area on the moon for that is the Marias Hills region. And it basically just is completely covered with multiple domes. And related to probably one of the last volcanically active regions on the moon. And here's just an oblique view of one of these domes. Now, I should mention that there are domes on the moon that are not related to Mare basalts. They have a different composition. They're not basaltic, they're silicic domes. And so if you're interested in additional volcanic features or special topics like that, then you could start by looking at the LROC featured image website, and then there's a lot of work that's been done on silicic domes on the moon. That's a really interesting topic on its own. But those types of features are more rare, and so for our activity today, we aren't looking at those. Okay, one of the other special things that you may have even heard about in the popular press in a couple of years ago are called irregular Mare patches, and these are thought to be either extremely young because they don't have very many craters on them. They're very smooth. We'll get back to that craters idea in just a moment. Or they're old and they represent some kind of a strange geologic process. And so this is another example where doing detailed geologic maps is sort of a helpful tool to trying to figure out what the geologic history is, and also looking at the regional geologic history. And so this is actually one of the current hot topics in lunar stratigraphy and morphology. Okay, another type of volcanic deposit are pyroclastics. And here in Schrödinger crater, we saw this earlier as an example of a multi-ring or a peak ring basin. As you might have noticed earlier, this little black cinder cone here in the center. It's oriented along a graben, and you can see there's other fractures graben that run through the crater. And this is basically a pyroclastic eruption that happened here. So there are these cool types of pyroclastic eruptions, and then elsewhere on the moon are larger, more regional, what are called regional dark mantle deposits that are really dark pyroclastic material. In actuality, they are black glass beads, green glass beads, orange glass beads. They basically have varying amounts of iron, titanium, and the black ones in particular have a lot of ilmenite, which is titanium oxide in them, or titanium iron oxide. And these materials are one of the things that's of particular interest for in situ resource utilization, because you can pretty easily break off the oxygen atoms to generate a source of oxygen. So when you hear about ISRU on the moon, this is one of the source materials that people are interested in. So pyroclastics, that might be something that you would end up with as an extra unit, a dark mantle unit on your geomorphologic map. And one other feature that we're going to see, it's not really a Mare feature. I mean, it's a little bit enigmatic where these swirls come from. You can see that we have these really nice high albedo features that are overlaid on the Mare basalt material. And the question is whether, I mean, they seem to be related to magnetic field anomalies. And so one question is whether it's related somehow to the Mare basalt itself, or the dikes that formed the Mare basalt. Are they magnetized, or were they magnetized in a way that allowed these features to form? Or do we see these swirls on the Mare simply because of the albedo contrast, and they are also are formed on Highlands material, which is higher albedo, and we just can't see them. This is another enigmatic feature on the moon that's currently being researched. So in your mapping area for this for the project today, we do also have some swirl areas. And so this will be one of the things you want to think about. How do you represent a superficial feature like a swirl on your map? Also, we have some more superficial type features. It's a kind of an overlay, perhaps. Here you can see that there are all these little chains and sort of herringbone patterns of small craters that are also in this area. Those are secondary craters that come from larger craters that are a bit farther away and have hit the surface at an angle. And so then they kind of skid along, or it's a chain of pieces of ejecta that make multiple small craters. And these secondary crater chains are something that, depending on, again, on what your scientific questions are for your area, that you might want to individually map, or you make an overlay that shows where you have a greater abundance of these secondary craters. So yeah, here we have an oblique view of Mare Ingenii, which is our study area for today. And you can see that we're going to encounter some of these swirls in our work. Okay, finally, kind of related to craters and volcanics, particularly Mare volcanics. Sometimes you might see a little crater that has dark ejecta. And what that may indicate is that you've punched through a light layer of material into some dark Mare deposit, and you've excavated Mare deposit. And so that's kind of another special case that depending on what your science questions are, you want to be on the lookout for. And here's just another example where on a Copernican crater, because we can see the rays in the ejecta really well, and there's a really nicely defined rim. Here on the high albedo ejecta, you can see that some smaller craters that excavate through that light ejecta and expose the dark material underneath. And so that's a dark halo crater. These ones are examples that are impact craters. Other dark halo craters don't have an origin that's necessarily known. They might be pyroclastic deposits or some other volcanic feature. And so that's also where more detailed geological investigation can help you figure out some answers. So then let's have a look through the highlands at what kinds of morphologies we can expect there. That's these high albedo, very cratered regions of the moon. And this is, maybe you're already thinking about this. More craters are older because the surface has had more time to accumulate craters, and fewer craters are younger surfaces. They formed at a later date and have much less time to accumulate craters. And this will become our next theme to look at how we can use that to our advantage. But I wanted to just point it out so you can have it already in your brain. So the highlands materials are anorthositic generally in composition, and this means that they have a lot of plagioclase and they do not have a lot of iron or titanium. And that's also a reason why they are light colored versus dark colored. And they also are generally higher in elevation than the Mare because they stand up high and they couldn't get covered with volcanic material. So these units are generally a bit rougher. And here you can see, for example, the Frau Maro formation. This is one of the ejecta units that formed during the formation of the Imbrium Basin, which is a big basin in the northwestern part of the near side of the moon. And so that's very rugged stuff because that's ejecta material. It ran out over the existing topography and basically makes this really knobby material. Then there's a slightly, I think this is IFS, which is slightly smoother, but also a highland unit. And you can see that it contrasts in morphology to the Mare basalt that's adjacent to it. Flat, smooth, and dark. Here's bumpy and higher albedo, higher elevation, and then compared with the Frau Maro, that's even more rugged. Then we've got, for an example, so a sort of a borderline Imbrium pre-Imbrium terrain, which stands up even higher and is more rugged. And if you had a bigger view of this, you would see that it has more craters on it. Then another example of a highlands terrain or kind of an intermediate terrain is here you've got this rugged Preambrian terrain surrounding an old plains unit. See, this is flat, has some fractures through it. But compared with the Mare basalt that's right next to it, you can see that there are a lot more craters on it, more craters and more bigger craters. So you would delineate the edge of this unit and say, okay, this unit is certainly older than this Mare basalt. Okay, and in this case, I believe this is from one of Wajia's Apollo landing site studies. She made this into an Imbrium's plains unit. Okay, and then sort of also grouped with the highlands because it's compositionally similar, but it's kind of a hybrid because the morphology is more similar to a Mare basalt, are these light plains. So the name says it all. They're light in albedo and they're plains units. So they're flat and smooth. Generally, however, they have more craters on them than the Mare basalts. And so we know that they're relatively older. And then the question is, how did they form? So in the process of doing maps, you would see that morphology is different, make a separate geologic unit from light plains, and then we can feed their distribution and their relative age information into ideas about how did they form. And in this case, light plains were originally theorized to be volcanic because they're flat plains. But when Apollo 16 returned samples from a light plains unit that were completely impact breccia material, then the scientists had to rethink about, okay, light plains, at least in that case, are not volcanic. They are impact ejecta. And so that's another ongoing question that Claudia has worked on and that we have another student in Münster who's working on is how do these form? But number one priority is we need maps. Then we can work and more carefully on the answers to those questions of origin. Okay, and then finally, a feature that you see often in the highlands are lunar scarps. These again are thrust faults, and they have a slightly different appearance than the wrinkle ridges, but it's actually basically the same process that forms it. And there are a few cases where at the border between Mare and highlands, you get a wrinkle ridge that runs into the highlands and then turns into a scarp in the highlands material. And so that's kind of a really interesting a tectonic topic. So I'm not sure that we have any scarps. I don't think we have scarps in the activity for today, but that's kind of a hot topic that you can certainly find more information on also in the popular press. And so here, just to kind of follow along our thinking about what's going on, cross-cutting relationships here. The highlands material here that formed, some craters, different ages, the scarp formed, okay? And then we actually we've got the ejecta that's covering, it appears to cross-cut the scarp in this case. But here we would want to very carefully have a detailed look at the relationship between the scarp and the ray here to make a final decision on what we think the progression of events is in this region. Okay, so now that you've looked at all the morphologies and you've made some decisions about what units you're mapping, I just want to show you an example of what you would end up with. Also taken from Claudia's South Pole Aitken map. You basically then marked everything and you have your oldest units marked in one class. This is the pre-Nectarian system. So this sort of the second oldest and oldest SPA materials that are separated from sort of the undefined pre-Nectarian materials. So oldest, next oldest, and then moving into younger areas where we have here in teal some of those light plains units, and in purple different Mare units, which we call dark plains units here. And then moving the next step up in time, or kind of the similar time frame, is the formation of the craters that have that age in the Imbrium system. And then the last step is the Copernican and Eratosthenian crater materials that are the most recent events. And so that basically all assembles into the geologic map that you have at the end. And each of those units is a geomorphological unit that you organized from oldest to youngest based on superposition and cross-cutting relationships, in addition to these the qualitative decision of the degradation state of the craters. Okay, so now the next question, and I'm gonna need to be a little quick here because we wanna then get to Greg Michael, who's gonna give us some more details about how you can use craters to fix some absolute ages to your time scale. And I wanted to start first with just to give you a theoretical overview, and then Greg is gonna get into some details about the math and also the practical application and fitting of the data that you get out of this method. So crater size frequency is a clock. I mentioned before, just so you could start thinking about it, that the older surfaces like the highlands have more craters on them compared to the younger surfaces with the Mare units. And we could see that the relative ages based on superposition and cross-cutting relationships are also highlands old, basin or Mare basalts young. Okay, but cratering is a process that can be modeled mathematically if you are assuming that it's a random process. If you know something about the flux of material that's coming in onto the moon, maybe you can do more than just the relative determination of ages. So basically we start now with the premise that the number of superimposed impact craters on a surface is directly related to geologic time. Okay, I think that's a pretty logical premise. And so I just state this again here. How can we use this to our advantage to give us more quantitative information about the ages of the surfaces? Well, you can go in and you can measure what are called these crater size frequency distributions in your different locations. And so the example here are for Apollo landing sites. And basically, if you do that, measure the numbers of craters. Well, you basically measure the diameters of all of the craters in your area, and then you make a plot of diameter against the cumulative frequency. So basically the number of craters in each successive bin accumulating to the smaller diameters. In this case, you can represent other ways too, but we'll just use the cumulative crater frequency here. Then you basically get a plot that looks like this, okay? And what you can see is that some locations, like here, the Apollo 16 landing site in this dark squares, they have relatively more craters than, for example, here, the Apollo 12 landing site in the dark circles, okay? And what that tells us is, okay, the distributions that appear higher in this plot are older surfaces than the ones that appear lower in this plot. Okay, so that's all well and good. We can now, with this plot, we can sort the ages of the Apollo landing site surfaces. But isn't there maybe there's this more simple way for us to represent this so that we can say in a text a specific value, as a reference. And so that was where the idea with this n of 1 number or value came, or you could also use a different reference diameter, because the n of 1 is the cumulative number of craters that are greater than 1 kilometer in diameter for each of those data sets. And basically you can just have this one value that you use as a reference for that entire distribution that you measured. Okay, now, but I don't want to go into a lot of detail here. I realize that I just put too many words on this slide, but basically to be able to do this in a, statistically good way, you have to also know something about the distribution of craters and the shape of this distribution so that you have some control on the quality of the count that you had and that you understand what it is that you've actually measured. And so what feeds into this process of figuring out this n of 1 is that you need to know what's called the lunar standard distribution. And so what you can see is that basically the distribution of the sizes of craters is not a linear line, okay? It's a function that is a bit, it's dependent on the size, the diameter of the crater, or the diameter, ultimately the size distribution of the impactors that are forming the craters. And so what we need to do is to basically have this standard distribution as a normalization step for determining our n of 1. And I think maybe Greg might talk a little bit more about the standard distribution. So how do we then generate from this n of 1? Because, okay, that's nice. We have one number now that we can say, okay, our A units 2.4 times 10 to the minus 4 per square kilometer. That's not very meaningful, for us as geologists. So how do we develop then an absolute age that we could use as a comparison and not just a relative estimate? And this is where Neukom and Hartmann and others did a lot of work in the late 70s and the early 80s to basically come up with a way of calibrating this n of 1 value to actual ages of samples. And so we have the Apollo and Luna samples, and now we also have the Chang'e 5 sample, where we have the ages, we have the crater size frequency distribution that we measured, and then also the n of 1 value that we can take out of it. Okay, and we can assemble then all of this information into a data set. So here we have age versus the number of craters less than 1 kilometer, greater than 1 kilometer per square kilometer. So that's the n of 1 versus the age of the sample as determined in the lab. And then we can actually go in here and fit and just the axis is flipped here because this is the kind of the historic version here. Then we can try to fit this data set with some functions. And you can see that it's not so easy. And Greg will certainly then have some comments about that. But this is where then we eventually get an absolute chronology and are able to then relate the n of 1 value that you can measure with your crater size frequency distribution versus the age. And then you would be able to ideally solve using your n of 1 at an unsampled part of the moon and for an age of your surface. Okay, and this was just to show that there's been a lot of different opinions about exactly how to fit this data set, and that's an ongoing hot topic in our part of planetary science. Also, you've certainly, or you may have heard and should be aware that this lunar chronology function is also modified for the moon, from the moon for Mars and for other planets. There are chronology functions based on things like the asteroid size distribution, but many of the chronology functions for terrestrial planets and also asteroids are based on the lunar, important that the lunar one be as good as possible, because the moon is the only place that we currently have samples from known locations that we can actually set up this calibration for. Okay, and so then we come to what is our final goal. It's to have a map with absolute age control so that you can then assign some numbers here to your ages of your units. So what you would do, this is the correlation chart that I showed you at the very beginning from Claudia's map sheet. You would go in and you could very easily then find yourself some count areas where you can measure the size frequency distribution of craters on your dark Mare deposit and actually determine an absolute model age, so you can really fix that age and also the range of ages that you want to assign it in your correlation chart. You can go in and find yourself, for example, in our paper with Misha Ivanov, he measured craters in Apollo Basin, which is a large basin inside of SPA, and was able then to fix the age of the Apollo Basin as being a slightly pre-Nectarian. Okay, and here you can go through, you don't have to count, and you won't be able to count craters on all of your geologic units, but you can cleverly pick units to give a framework for your entire map that then allows you to translate your map from relative ages into absolute ages, and then to achieve the final goal of understanding the history of your part of the moon, the history of the moon, and then also how the moon and your study area fits into the context of the history and development of the terrestrial planets.